In this chapter, we're going to talk about gases, and specifically in this video, we're going to talk about the gas laws. So gases are the state of matter that have no definite shape or volume. If you transfer a gas into a larger container, it will fill the size of that container, rather than staying the same volume that it was in the original container. Gases change their volume also with temperature and pressure. If you mix two gases together, or more than two gases, they will form a homogeneous mixture, which means that the mixture looks the same throughout. It's uniform throughout the mixture. They are less dense than solids or liquids, and gases typically have little interaction between molecules. So when we talk about the gas laws, we will talk about gas pressure. Gas pressure is defined as force per unit area. So for example, if we look at our barometer here, the air pushing down on the mercury forces that mercury up into a column, and we can read the column, the height of the column, and determine the air pressure. So the pressure comes from the air putting force on this area where the mercury is in this container. Atmospheric pressure is the mass of air that presses down the Earth's surface. So we typically measure this in ATMs, hence the fact that the mass of air pressed down the Earth's surface happens to be 1 ATM, because we define it that way. Of course, there's some variation depending on where on the Earth's surface you actually are. Putting that into other units, we can measure atmospheric pressure in pascals or kilopascals or millimeters of mercury or inches of mercury or any other variety of units. So this table here shows the conversions between different units of pressure. So a couple that I would expect you to be familiar with are 1 atm is equal to 760 millimeters of mercury, and 1 atm is also equal to 760 torr. Those are used frequently enough that it's worth your while to memorize those. And they both happen to be 760, so you just have to remember that 1 atm is equal to 760 torr, or 760 millimeters of mercury. The rest of these you do not need to memorize. You would be given those if you needed to do the conversion. And there's also a set of these in your book, so if you're working on them for homework or for a practice problem, then you can look those up. So the four variables that we look at when we talk about gases and when we look at the gas laws are pressure, temperature, volume, and number of moles. And you can see we got very creative with the abbreviations for these. P is pressure, T is temperature, V is volume, and N is number of moles. So we don't use M for moles because M can also be used for mass. So to avoid the confusion, we use N for number of moles. For all of the gas laws, temperature must be in Kelvin. Kelvin is the standard unit of temperature. It's an absolute scale, so all of the gas laws were measured based on absolute temperature, which is Kelvin. So let's start going through the gas laws. So first up we have Boyle's law, which looks at the relationship between volume and pressure. Now whenever we look at the relationship between two of the variables, we keep the rest of the variables constant. So the relationship between volume and pressure, this symbol here means that these are proportional. So volume is proportional to 1 over temperature. In other words, volume is inversely related to pressure. So if volume goes up, that means pressure goes down. If pressure goes up, that means volume goes down. So we can write this as pressure times volume is equal to a constant, or the form that's more useful to us is the P1V1, which is our original pressure times our original volume, is equal to P2 times V2, so our new pressure times our new volume. If you look at a graph of volume and pressure, you will see that they're inversely related. They do not form a straight line. They form this curve that kind of goes backwards here. If we do one of these as 1 over whatever our variable we're talking about, in this case we do 1 over pressure, so in other words inverse pressure, we then get a straight line relationship between the two. So let's take a look at an example problem here. We have O2 is in a 49-liter container at 150 atm. At 1.02 atm, what is its volume? So we're going to use Boyle's law because we're dealing with pressure and volume. So P1 is given to us as 150 atm. P2 is 1.02 atm. Let's actually write P2 on the other side here. V1 is 49 liters, and V2 is what we're trying to determine. So we have P1 V1 equals P2 V2, and P1 is 150 atm. V1 is 49 liters. So then we rearrange this to get V2 by itself. So V2 is equal to 150 atm times 49 liters divided by 1.02 atm. So if you divide that out, that comes out to 7,210 liters. So let's talk about the next gas law. So the next one we're going to look at is Charles's law. Charles's law includes volume and temperature when we keep number of moles and pressure constant. So this tells us volume is directly proportional to temperature. So volume is directly proportional to temperature. So if you make a graph of volume versus temperature, you will see that it is a straight line. So these two are directly related. So volume over temperature is equal to a constant, is the original form of the law. Or what's more useful to us is V1 over T1 is equal to V2 over T2. So let's take a look at an example with Charles's law. A balloon is inflated in a room that is 24 degrees Celsius and has a volume of 49 liters. The balloon is then heated to a temperature of 58 degrees Celsius. What is the new volume if pressure remains constant? So if we determine our V1 and our T1, V1 is given to us as 4 liters, and T1 is given to us as 24 degrees Celsius. But remember, we always have to put temperature in Kelvin for the gas laws. So if we add 273 to 24 degrees Celsius, that gives us a total of 297. V2 is what we're trying to find. And T2 is 58 degrees Celsius. So if we add 273 to that, that comes out to 331 Kelvin. So we have V1 over T1 is equal to V2 over T2. So if we plug that in, V1 is 4 liters, T1 is 297 Kelvin, V2 we're trying to find, and T2 is 331 Kelvin. So the way I always advise you to do this is to cross multiply. Because if you have the unknown on the bottom, that's really the best way to work it out to get the unknown by itself. There are other ways you can have the unknown is on the top, but to be consistent, I always show you to cross multiply. So if we cross multiply the side with the unknown, that gives us 297 Kelvin times V2 is equal to, and then we cross multiply the other direction, and that gives us 4 liters times 331 Kelvin. So then we want to get V2 by itself. So we divide both sides by 297 Kelvin. And that cancels out that. And we're left with V2 is equal to 4 liters times 331 Kelvin divided by 297 Kelvin. So if you put that into your calculator, you come up with 4.5 liters. Now, when you're determining significant figures with the gas laws, ignore the temperatures. Use the other variables to determine your significant figures. Temperatures are not very precise, and they're actually not really a good way to determine the significant figure. Sometimes you get problems that have the temperature to one significant figure. Obviously, if we were doing this in a case where we really needed accuracy, we would measure the temperature to more than one significant figure. So for the purposes of the gas law, ignore the temperatures and just deal with the significant figures from the other variables. So Avogadro's law is very similar to Charles's law in that there is a direct relationship. Avogadro's law looks at volume and number of moles, where we keep temperature and pressure constant. So volume, and let's put this in a color that shows up a little bit better on the background. So volume is directly related to number of moles. So another way of putting this is volume over number of moles is equal to some constant, or again, the form that's more useful to us is volume V1 over N1 is equal to V2 over N2. So I'm not going to show an example problem for every single one of these because they're very similar to how we work out Charles's law. So we will get more practice with these in class, but we're going to go ahead and finish discussing the gas laws in this video. So Amundsen's law looks at pressure and temperature. So we've already done pressure and volume, we've done volume and temperature, we've done volume and number of moles. So now we're going to get to pressure and temperature. So of course we're keeping the number of moles and volume constant since we're varying pressure and temperature. So pressure is directly related to temperature. So pressure over temperature is equal to some constant, or in other words, P1 over T1 is equal to P2 over T2. And finally, we get to the ideal gas law, which relates all of the variables. So the ideal gas law tells us that pressure times volume is equal to the number of moles times the gas constant, which is represented as R, times the temperature. So PV equals nRT. The gas constant that we use for the ideal gas law, there are actually several different values for the gas constant. You do not need to memorize them. They will always be given to you. So R is equal to 0.08206 liters times ATM over Kelvin times mole. So we can also define the standard temperature and pressure for gases. Standard temperature is defined as 0 degrees Celsius or 273 Kelvin. We say 273.15, but most of the time we just round off to 273. And pressure, standard pressure is defined as 1 atm. So if you rearrange the ideal gas law for volume, and you substitute in 1 atm and 273 Kelvin, then what you find if you have 1 mole of gas at STP, which is 273 Kelvin and 1 atm, the volume of 1 mole of gas is 22.4 liters. Now this is only true at STP. So if you are working a problem that involves some stoichiometry, and you have to figure out the volume of gas of a certain number of moles of gas, if it happens to be at STP, you can use the relationship 22.4 liters, 1 mole equals 22.4 liters. Now, this calculation was worked out with 273 Kelvin and 1 atm. If your situation and your problem is not 273 Kelvin and 1 atm, this relationship no longer holds. But if you do have those variables, you do have standard temperature and pressure, then you can use this as a shortcut. So let's look at an example where we have to calculate something with the ideal gas law. We want to know here how many moles of a gas are present if the gas occupies a volume of 300 milliliters at 35 degrees Celsius and 789 millimeters of mercury. Now you will notice, if you think back to what R is equal to, that we're going to need volume in ATM, pressure in ATM, volume in liters, and temperature in Kelvin. And we do not have any of these variables in the correct units. So we need to do some conversions here. So we'll start with pressure. Pressure is 789 millimeters of mercury, but we need this to be an ATM. So if you look back at the slide that has the conversions, 1 ATM equals 760 millimeters of mercury. So 789 divided by 760 comes out to 1.04 ATM. And then if we take the volume, we have a volume of 300 milliliters. And we know that there are 1,000 milliliters in a liter. So 300 divided by 1,000 is 0.300 liters. And then our number of moles we're trying to calculate, R is the constant. Temperature is given to us as 35 degrees Celsius, which we have to convert to Kelvin, so we add 273, which gives us 308 Kelvin. Now, the rest of these variables were a matter of dividing by 1,000 or adding by 273. But if you look at your pressure, that does not come out to exactly 1.04 ATM. We've rounded that value off. So make sure that you keep that value in your calculator so that you can use it when we work this out. Because if you round off here, you're going to get some slight error in your final answer. Now I'm going to have to erase this in order to have room to work out our problem. So we have PV equals nRT. So if we plug this in, we have 1.04 ATM times 0.300 liters is equal to the number of moles times 0.08206 liters times ATM over Kelvin times mole. And the temperature was 308 Kelvin. So then we rearrange this algebraically. Over Kelvin times mole. So that cancels out and we divide by the same thing on the other side. And so N is equal to 1.04 ATM times 0.300 liters divided by 0.08206 over Kelvin times mole and 308 Kelvin. So when you put this into your calculator, bring up the value you have for pressure, multiply that times 0.300, and then divide by 0.08206 times 308. And you should come up with 0.14 moles. Okay, so let's look at an example where we combine some of the gas laws. So we have compressed air tanks have a volume of 8 liters and a pressure of 140 atm at 20 degrees Celsius. And we want to know the volume of air in the tank at STP. So remember we said earlier STP is 1 atm and 273 Kelvin. So we have volume, pressure, and temperature. And then we have temperature and pressure and want to know the new volume. Now, we could go through the ideal gas law and calculate number of moles for the first set that are given, and then go and plug that in for the second one and calculate the volume. But that would be a lot of work. So there's a quicker way to do this. We know from Boyle's law that P1V1 equals P2V2. And we know from Charles's law that V1 over T1 is equal to V2 over T2. And we know from Hamilton's law that P1 over T1 is equal to P2 over T2. So we can put all of that together to say P1 V1 over T1 is equal to P2 V2 over T2. And that gives us a combined gas law that we can use to calculate an unknown volume here. So I'm going to again erase all of this so that I have enough space here to work this out. So we have P1 V1 over T1 equals P2 V2 over T2. And we have a P1 of 140 atm, 20 degrees Celsius, we're not there yet, we have a volume of 8 liters, and 20 degrees Celsius. We add 273 to that, we get 293 Kelvin. P2 is given to us as 1 atm. We're trying to find V2, so we don't know what that is yet. And T2 is 273 Kelvin, because we're at standard temperature and pressure. So then if we cross multiply 293 Kelvin times 1 atm is equal to 140 atm times 8 liters times 273 Kelvin. And then we divide both sides by 293 Kelvin and 1 atm so that we get V2 by itself. 293 Kelvin divided by 1 atm times 1 atm. So V2 is equal to 140 atm times 8 liters times 273 Kelvin. Divide that by 293 Kelvin times 1 atm. And if you multiply that out, you should come out with 1040 liters. Okay, so we will stop here and we will get some more practice with this in class.